Welcome, everyone, to our live webcast, Advanced Calibration Techniques Based on Loop Testing, co-hosted by ISA and Beamex. Thank you for joining us. My name is Mike. I'll be the operator for our presentation today. Now, before we get started, I would like to take a moment to acquaint you with a few features of this web event technology. At any time, you may adjust your audio using any computer volume settings that you may have. On the right-hand side of your screen, you see the Q&A window. There's a large window which holds all of your sent messages and a smaller text box at the bottom where you can type in your questions. To send a question, click in the text box and type your text. When you're finished, click the send button. All questions that you submit are only seen by our presentation team today, and your questions will be responded to at various times throughout the presentation during our Q&A sessions. At the conclusion of today's program, we ask you to complete a brief post-event survey. If you would take a moment to complete this survey, as it will help ISA plan future web events. We are joined today by two speakers, Ned Espy and Roy Tomolino. Ned Espy, Technical Director, has been promoting calibration management for Beamex, for over 20 years. Ned has helped develop best practices for calibration with a focus on pressure, temperature, and multivariable instruments. Roy Tomolino has been teaching calibration management for almost 20 years. Throughout his career, he has taught on 4 different continents to people from over 40 countries. At this time, I'd like to turn the presentation over to our presenters to begin. So welcome, gentlemen.
Hello, thank you, Mike.
Thank you, Mike. Yeah.
So I just have to say this. So Ned is he's the one that you want all the good practices, all the good ideas, and I'm the one that's a good example of a bad example. So just wanted to point that out right off the bat.
Thank you, Roy, for that information.
Yeah, sure.
So I see we have a slide here about our annual calibration exchange, ACE. Do you know anything about it?
You know what? You should know something about it. You've been there 5 times in a row now. So ACE, where are we doing that this year?
In lovely New Orleans. Be nice and cool.
Yeah, right, New Orleans. So this is where we have the great minds in calibration coming together. And do we know what some of our topics are going to be?
I know we've got that multivariable workshop is listed, but we have somebody from Emerson.
I'm looking forward to that one.
Yeah. And we have a good lineup of speakers, so hope you all can make it. And there is advanced registration this month.
Right. Get signed up by August 20th to get that discount. Yeah.
All right. So shall we move on with our presentation today?
Good thing.
All right. So let me go through the agenda. Just have a brief introduction. Want to make some points about what's happening in the calibration arena with process control. And since we're talking about loop calibration, just want to make some definitions and get everybody on a sort of a level playing field. And then Roy's going to make a demonstration of a simple loop test, and we'll open it up for some questions and hopefully some answers. Then we'll transition and talk about how do you analyze loop error. You know, how can you do the math to effectively analyze things, and talk about possible examples or potential examples of where you might use this technology or this method. And then Roy's got a more complex demo. I think you'll find it very interesting. So then we'll wrap it up. And if we run past 1:30 with the question session, we'll try to keep going till we run out of questions. Okay. So before we get into the PowerPoint presentation, we do want to ask a question. How many out there are utilizing loop testing today? So pretty simple question. If you don't know, certainly pick that. All right, so very interesting. The results are coming in, but it looks like a high majority utilize loop testing. That's good to see, almost 75%, and maybe 20% or more, slightly over. The other 25% aren't utilizing it or don't know if you're utilizing it. Okay, well, that's good. We'll see what, so we should have some good knowledge out there when, as we go through this, and maybe during the Q&A you can teach Roy and I some things.
Yeah.
Okay. So just in general, when you talk about performing calibration in your facility, so many times when I visit a client, this is the way we've always done it, and when they talk about doing something different, it's kind of a big shift. So just because you've always done something one way doesn't mean there maybe are some better practices you can bring to the table. Also, from our perspective as a calibrator manufacturer, the technology is just moving really fast. Sensors are getting more reliable, more accurate, so maybe you don't have to calibrate certain things as often as you used to. But everybody's still calibrating. There's a lot of activity in this area. But and also there's less man hours or man time available to perform calibration, so you need to come up with more efficient ways to test and get good coverage in your facility when it comes to calibration and your maintenance. So while loop testing is not like something radical or new, it's been around for some time, and there's many people out there using it. So we just want to bring it to the fore today and put our perspective on it, but know that it's just another way to perform some testing and maybe gain some efficiencies. So let's move on. So let's talk about just a basic loop. This is really simple, where you have a temperature probe, maybe in a thermal well or embedded in a pipe, going to a temperature transmitter. There may or may not be a local display. The display may even be built into the transmitter nowadays. But then the 4 to 20 signal is sent on to your control room or, single loop controller, whatever, PLC, whatever that might be. So, this could be off a little bit. This probably isn't affecting the signal. But then this has an input card, so, this could drift as well and cause some potential error. So there's the element, the transmitter, and the DCS input are the three components in this simple loop. And to make a good measurement in the plant, if this is, let's say this is drifted positive a little ways, but the DCS inputs drifted negative a little ways, you might have a very good measurement taking place. Temperature elements, thermocouples, RTDs, they also tend to drift and eventually fail. So this is something else you want to consider. But end to end, if you're making a good measurement, if what you're simulating or measuring here accurately in the field is being displayed in the control room, it doesn't really matter what's happening in between. So that's the idea of a loop test. Now, there's always a problem, and temperature is a good example. What if this probe really can't be removed? So a closed loop, that's kind of a term I've coined, is the best method or best practice you want to do end to end. But, so if you can't do that, then, in this case, there's three elements. We're going to remove one element and then simulate a signal in here. So if you have to do that, you need to try to think of a way to even check this, even if it's at process temperature. And for example, if you could have a parallel thermal well in place where you could temporarily insert an accurate temperature probe, you could get a ballpark reading to compare to this guy. And if you're documenting it, if there is some kind of difference, let's say it's a difference of 2 degrees or something, is it getting wider or moving? Are the two measurements moving apart every time you go out and make that check? But Roy has some comments on this too. This is, this concept here is open for discussion. So Roy, what do you what do you have to say here?
Well, so doing a closed loop test is definitely the preferred, but I've run into some scenarios where I'm going to say it's impossible to actually pull that temperature probe out. I had an example where the probe was 9 feet long, and even with the shutdown, you'd have to disassemble the machine in order to get that temperature probe out. So we're trying to deal with that here and give you some ideas of what can you do. Can you do a 1-point check at least with your existing temperature probe? But we're opening up the loop at that point, and we're testing the transmitter. And in the example given just a little bit, we'll test the transmitter and the 4 to 20 all the way out to the local display or the DCS display. So that'll be our temperature loop that's coming up soon.
And Roy, you and I both were at a plant where they were doing this exact test. They couldn't remove the probe, but they were connecting the probe up to the calibrator, and were able to compare that number to some other probe that was in the process, so they could get, like a comparison check. So yeah, you need to be creative when you can't do the end-to-end or closed loop kind of test.
That was a good idea.
Yeah. All right. So, Roy, why don't you show us, a simple loop test and how it might look?
Why do I have to do this? I think I did the last one, so this time it's your turn. Okay, fine. So I will do a demo. I do have this one is a Honeywell temperature transmitter. It's set up as a 3-wire RTD, and my RTD leads. Am I actually sharing my video?
Yes.
Is that working? Okay.
Yes.
So I do have a set of leads that I've had created for me, and these are what I use for testing RTDs. I've got the banana plugs on one end, and then I piggyback them, and then I have my 3 or 4 connections here. If it's a 3-wire, I just leave my 4th wire off. And I'll connect on the plus and the minus here to the calibrator as well. And just so you see, I am using an MC6 calibrator here. What you're seeing on the screen that's a remote controller, so you're literally seeing what I'm seeing on the calibrator. So this is not a pre-programmed event. You're actually seeing what's going on with the calibrator. Now, this temperature is my TT345. I've got 2 different tests. One of them is a test for the transmitter, and that's my TT345, this guy, where I've got my temperature input and 4 to 20 milliamp output. The other one is my loop test. And let me back out of here. So my loop test, I have a separate tag named for it, and it's called TT345 loop. And I'm generating temperature into my transmitter, and then the 4 to 20 is going out over to the DCS. So I'm keying in what the DCS display is showing here. You know what? I need to connect my power from the transmitter, and if I look in the middle of my screen, plug this in here. All right, I'm going to go red to positive and black to negative, if that's okay with you all. All right. Oh, my connection just came off. Gotta love live events. All right, hang on a minute.
Roy, here on the indicator, so on the transmitter side, you'll power it and see the milliamps.
Yeah, I've got a loop power actually set up on this, on my indicator. let me back up a second. So I put in to give me a loop power on here, Ned. And, of course, I didn't save it. Let me put on my loop power here so I can power up my transmitter right from here. There we go. I thought it was going to save that setting for me. So we've got 0 degrees in, and I'm waiting for this transmitter to boot up. And I'll use the display on the transmitter as my hypothetical DCS display. So doing this calibration, we're simulating a loop calibration where we're simulating temperature through RTD, through the transmitter, and then the 4020 goes out to the DCS. And this does have a local display, and I don't know if you can tell, but it's showing 0.3 right now as far as degrees. So I have 0 degrees input. Oh, you know what? I need to hit start. So I'm keying in my 0.3 degrees. This is my DCS location. We're getting a live error of 0.06% of span. My tolerance is set up for 0.5% of span. Let me accept this point. Now the temperature is moving up, so I'm feeding it 125 degrees, and at the display, I'm getting 125. It's juggling between 3 and 4. It's most often a 4, so 125.4. So my error is 0.08%. Let me accept this point. I'm feeding it 250 this time. Yep, this one is a .4 as well. So my output is 250.4 degrees, and it's calculating what my error is, 0.08% of span. I'll accept this point. So again, I'm doing a loop check with a temperature transmitter as the starting point, and the end point is a DCS display. And on my display here, I'm getting 375.5. And the final test point is 500 degrees. And this one is 500.5 degrees. I'll accept this test point. So this is our loop check. This is including the transmitter, the 4-20, all the way out to the DCS. And it's saying that we passed 0.1% of span was the error. And I'll go ahead and put my name in here as who did the calibration. Here's our graph. So we can see the blue lines represent our tolerance. So as long as our dots landed within the blue lines, then we know that we had a successful test. And this is all the raw data that we don't have to write down. Environmental conditions, so the barometric pressure is 12.358. I'm at about a mile-high elevation is the reason for that. So I'm talking to you from Colorado. So the humidity, we'll put it at 35%. All right, and we'll save this guy. As long as it's done and complete, we can save it as both, as found and as left. So I'll choose save as both, and I'll hit the check mark, and I'm done. So my test is complete. I've got a test result for the entire loop calibration, and let me go back here. If we wanted to or needed to, we could perform the calibration of just the transmitter itself. And Ned, I'm thinking maybe right now I shouldn't do this cal as far as just the transmitter. We could. Do you want me to run through that calibration? Or shall we just roll through?
Well, I'm thinking you're going to show it maybe the next demo, but I
sure will.
Some comments here. You were doing a partial loop test. You were simulating into the transmitter. So ideally, you would have liked to have been able to pull the RTD out of the process and maybe drop it into a dry block.
Yes.
Or bath and simulate those temperatures and then call the control room and see what they were reading. Or
that would have been the
nowadays,
most
a lot of people
we could have done.
Yeah, and a lot of people even have the ability to see the DCS readout on their phone. So, you can sit there and do that test by yourself. But so if you'd have pulled the probe and done a 3-point check, I mean, that might have taken 15 minutes just to run the dry block, plus the time to pull it out of the process. And then after you're done, and some more minutes to put it back in service. So doing a loop test can take more time, but if you saw those kind of numbers using a dry block, what you just documented, nobody's going to argue that you're not making a good measurement. I mean, you're within half a degree of the process, and that's that's going to satisfy most any control engineer.
Agreed.
So that's the basic concept is, do the best you can. You might not be able to do the end-to-end test, but if you're seeing what the final readout is, that's where you're making all your control decisions, and it's really a high quality. You're testing the whole measurement system at one shot. And if the loop does need adjustment, then you do have to break it down and look at the different elements. So in your example, you could either replace the probe, calibrate the transmitter, and also check the 4 to 20 input and see if it's on spot.
Yeah, there could even be an offset in the DCS itself.
Right.
And
they're pretty reliable.
To prove that.
Yeah, they're pretty reliable, but sometimes they're the culprit. Okay, so
I've seen that instead of actually calibrating a transmitter or fixing the probe, I've seen them put an offset in the DCS to zero it out.
Well, that's a good point, Roy. We have a customer that has a batch process with 6 zones. So he's got 6 RTDs coming into a PLC, 6 PLC inputs. And he was having all kind of quality problems. And we used a dry block and looked at the PLC readout. He was putting in offsets so that all 6 zones were identical to that dry block temperature versus the readout. So he actually had a quality improvement in his process. It really got rid of some huge headaches. And maybe, if the dry block's off a 1/10 of a degree or whatever, he has all 6 zones, measuring the same exact temperature. So there's a lot of cool things you can do especially with a temperature probe, because they can cause you all kind of headaches.
All right.
So I guess we're ready to move on to Q&A. I think that's our next slide, right? So does anybody out there have any questions? I'm not seeing any questions. Do you see any, Roy?
Yeah.
Just as a reminder, very quickly, Q&A located on the right-hand side of your screen. If you'd like to submit a question, type your question in the small text box at the bottom. When you're finished, click the send button. And again, those questions will appear for us as well to verbalize and then respond to. And Roy, I know you're seeing the questions, so perhaps we'll just jump into what questions we've received to this point.
Well, I'm deciding whether to mention, so it looks like on the Honeywell transmitters there is a tool called Advanced Device Commissioning.
Yeah, I'm seeing that question now.
Okay. So what are our thoughts on the tool? I don't have any experience with that tool as far as for doing a loop check on commissioning. Ned, do you have any comments on that?
I know different vendors have methods to check the probe, but they're mainly to see if the probe is getting ready to burn out. You can look at the millivolts of a thermocouple, and if it's moving, you can kind of predict that it might have a problem. On this particular question, it's saying, the question is, it leaves the process sensor out. people know their process, they know their sensors, their temperature elements, so they probably have a good sense if they're good or not. But I would say in this case, what's being described is an open loop. It's not a closed end-to-end loop check. So maybe you could do some validation and see if not testing the sensor is causing you're seeing some errors there. So it's certainly a tool to utilize, but I would check that sensor somehow, some way.
That kind of feeds into the next comment by Julio. Julio mentions our corporate procedures mandate to simulating the process variable, so pumping up a differential pressure cell physically to at least a 3-point calibration. So that way you're exercising the transmitter. I fed this transmitter the equivalent resistance for an RTD temperature, so it's essentially exercising the transmitter as well.
Right, but I guess for this procedure, if we're doing temperature, it seems logical to me you would want to try to put that probe in a dry block, and you're simulating temperature to the actual probe and doing the loop check. So the same, whether it's pressure or temperature, you need to exercise the primary element making the measurement. Okay, so then we have a comment here from Leo Staples, who helped author the recommended practice for management of calibration for ISA. And he's just saying that he's a longtime supporter of loop testing, which is good. And if you're interested, you could email me, and I can give you a link to the RP 105, the Recommended Practice 105. It was published, I believe, a year and a half ago by ISA, and a lot of good people were involved in it, putting a lot of ideas together. So you should check that out if you're trying to establish or upgrade your calibration management system at your facility.
Next we have James. Are there any ISA 84 or SIL level issues to consider when choosing end-to-end loop testing as opposed to separate component calibrations for SIS devices?
I'll let you handle that, Roy.
What, really?
So neither of us are SIS guys. We did have an expert with us last year. Maybe watch our reliability webinar we did. So I guess when you're evaluating SIS, there are some calculations. I don't know if when there's multiple devices in there, it should be considered. But to me, from a reliability standpoint, if I'm checking out a safety system, a shutdown system, or an interlock, checking the end-to-end that makes that interlock activate or go to a safe mode. That, to me, that's critical, that you're checking all the components in the loop. Let's see. So, gentleman, Brian is acting. What's the lifetime on an RTD? It all depends on your process. If you have a harsh process, and the construction of the RTD, is it? I guess the more rugged an RTD is made, perhaps the less accurate or the less responsive it is. So there's just a lot of variables as to how long something will last. So you might can buy something cheap and fragile for certain applications, but you need to buy maybe something a little more expensive for other applications. So I really can't answer that question.
One thing I would say we do have more experience with reference probes themselves, or reference and RPRTs, and those you do need to be careful. If you have a very nice temperature standard probe, you never want to let it go and drop it into the insert, into the temperature block. You don't want to fracture the crystalline structure, because that over time, if you end up dropping it, I've seen people take the RTD and just kind of like smack it against the table as they're bored, and that's not good either.
No, that
will make your probe less accurate. Yeah, it was not me.
Yeah, but probes are made to be more rugged, and as I said just a moment ago, there's a compromise. They're probably less responsive or not quite as accurate as like a reference probe is more fragile, but you're getting an extra decimal out of it or whatever.
Yeah.
So here we have a question.
Here, are these demos available for future use? I think that means we are recording this, and the recording will be available so you can replay this. And you can skip past all the stuff I say and go right to what Ned says, which is what I would do.
Okay. Yeah, so then the next question is asking about loop power. Is there a difference using the calibrator power or the control DCS power? In general, no. If you look at the specifications of a transmitter, it says they operate from like 9 to 30 volts DC. You could use some 9-volt batteries, some 9-volt batteries as a power supply, and it should not affect the transmitter. So it's only if you're on the edge, if you're at the 9 volts or the 30 volts, or if the power supply can't power all the things that are in the loop, but there's multiple devices in the loop, or it's something kind of weak, and at some point the 4 to 20 will saturate maybe at 15 volts or 15 milliamps or 18 milliamps, not get to the 100% level. But I don't see that as a big issue in general.
Agreed.
So, Roy, this one looks good for you. Can you go over the percent of span and percent significance terminology? So that was on our calibrator.
Can we bring up I'd like to share my screen, Mike. So this was the test that we just completed. The maximum error was 0.1% of span, and our span is 500, 0 to 500. So 0.1% of that was our error. The significance is how much of our error did we use up in this error. So we used up 20% of our allowed error
tolerance.
Budget?
Yeah.
Tolerance. So you can use significance to do things like, you know what, if it passes but the error is greater than 80% significance, you could give the technician a message to trim or adjust the transmitter. You could say it passed, but adjust the transmitter if it's greater than 80% significance. So that's useful in cases where you might deal with recalls, maybe in pharma, where you actually don't want an out of tolerance. You don't want a failure. So before you get to the out of tolerance, you make an adjustment before it hits that. So that's something you can use significance for.
Yeah, like in the pharmaceutical industry, if there's a failure, also nuclear power generation, if there's a failure, it means lots of paperwork. So it's not catastrophic. It could be, but it just causes a lot of headache for the maintenance people. So you might want to have when the significance of the error is at halfway out, you want to adjust.
Yeah, maybe even that.
But
this
we've
will
also
help
made
you head
many.
that off at the pass.
Yeah, but we've also made many presentations, it's not good to adjust every time. If something, in this case, it's only 20% of the way out, it could be because it was installed on a cold day in Colorado, and today it's a nice, beautiful day, ambient temperature in Colorado. So it could be off just due to environmental conditions, or it's just the conditions of that day. You could go out, a month from now, and it's out by minus 10%. It's like it's moving back. It's going up and down, which is good if it's staying within your tolerance. But if you're seeing, 20% today, you go out 6 months from now, it's at 40%, you leave it alone. You go out a third time, now it's at 60%. Now you've got kind of a documented trend going on. And so not adjusting is a good thing. So Beamex presents this term significance to help you make a good decision, for how you're wanting to work. Great question.
Just one final comment on that is that I don't, for the majority, I don't recommend you even use this. It's my personal opinion that running something until it fails and then do an adjustment is what I'd recommend. I gave this as a recommendation in case you're in pharma where there's a lot of paperwork involved in a failure. All right, I'm going to stop sharing here.
Okay.
Hannah, there's a question on an FB.
Yeah, we'll have to get to that one afterwards.
Yeah.
So here's a question about a dual RTD. So obviously you can only check it one at a time, and then simulating the rest of the loop. I don't have a lot of practical experience with dual RTDs. I mean, you're using them different ways. Some people are averaging the signals. Some people are looking for a deviation. If there's a deviation, that's a highlight that something's going on with at least one of the probes.
Right.
And then there's also the system has good. I mean, the systems today, the transmitters today, can make really good decisions. So if one RTD is bad, you've got the backup there. So it's pretty cool stuff. So in that case, you can do your loop test, but then you might need to, when you go to analyze a problem within the loop, you're going to have to check both probes at the same time. Maybe you could have a dry block with two holes where you could drop the probes in at the same time and check them. Any other comments on that one, Roy? That was pretty tricky.
No.
And this next question has to do with temperature indication. And, I mean, you can use any calibrator to simulate, an RTD signal into your transmitter. And but if you're doing a loop test, you're not really worried about the 4 to 20. You're checking the final readout, wherever that may be. So I think that question, instead of using an MC6, you could use any calibrator, as Roy used our calibrator to simulate a signal into the system, into the transmitter.
True statement. Yeah.
Okay, I think we're done, Roy. No, here's some more. I got to scroll. Wow.
All right.
Is there any mathematical basis to conduct loop calibration check with an RTD in the process if a previous RTD loop in the process at the same location has been checked? Sounds to me like it's two different RTDs, so if it's at the same location and you're getting the same readout on the second RTD, I would say no, you don't need to do a loop test. And maybe it's not really calibration, but you could document what that other readout was and just show that it's within, tenths of a degree or whatever the difference is. So that would be a time saver. Why, if there's something, right next to each other in the process, there's no point, and it's difficult to pull it out. You could do a comparative documentation. You're not adjusting anything. You're just verifying that it's also in the same ballpark as the one you are testing. So so there's a situation where you just need to use common sense and apply logic, and you can save yourself some time instead of doing everything. Do some verifications, and you can you can satisfy any auditor or any control room engineer. Okay. So if somebody says they want that recommended practice that Leo Staples mentioned, we'll make that available to you folks. Wow, these are good questions. So here's somebody who's using a Sierra 205 that uses 2 RTDs for flow calculation, testing open loop at RTD insertion, then at computer, then at DCS. I have to check each segment. I don't know if the flow computer is sending good milliamp output or if my DCS is receiving it, so I'm checking each segment. I may pull RTDs from thermal wells and check ice point on each. So that's a good, that's all a good method, and I'm not totally familiar with the equipment here, but, doing an ice bath check is very valid. If an RTD is off, it's typically off the same amount from 0 on. So if it's off, 1 degree at 0, it's probably 1 degree across the board. So doing an ice bath check is a valid way to, check a probe quickly. And for the other things described, if you're checking multiple things, it's almost like the other question. If you can kind of validate, I'm going to use the word validate, that things are working in parallel. The DCS is getting the system, the flow computer is getting the same number. So if you validate those things, you don't have to test them all the time. Maybe once a year, once every 2 years, you do a total check and you just do a partial check because you've proven that these numbers all match up when you have done a complete test. So just trying to help people save time. Look for ways to save time and make a good case to your management. So this one's kind of interesting. Roy, are you seeing this one about using the Hart loop test method and the signal isn't matching through to the DCS?
So I was having trouble reading that. So is that what?
Well, I'm going to say that the loop test method, I think, is a good method for checking that the wiring's good and that you've maybe put the transmitter back in service properly. But keep in mind that you're not shooting exactly 4 milliamps and 20 milliamps. You're at the mercy of the transmitter and the DCS input. So you should only expect things to be close. If you see a deviation that you're not happy with, the only way to really fix the problem is to check the PV versus the 4 to 20 output on the transmitter, and then do a separate check on the DCS input. hitting it with a very accurate 4 and 20 milliamps and seeing what the engineering units are on the display. So the loop test, to me, I like it mainly as a last thing to do, and it kind of verifies everything's in good working order. You're not so concerned about the accuracy of the readings.
Yeah. Just to confirm, a loop test is not a calibration. It's nowhere near.
Okay, I think, Roy, we should move on. I think it's time to move on,
okay.
Roy.
Yeah.
I've made a note of where we're at. We can start here when we come back at the final round.
Okay.
So hopefully we passed on some good comments to you guys. And by the way, this slide deck that we're showing today is from a paper I wrote several years ago. It was featured in the ISA InTech magazine, and we kind of updated it really in the last 2 months here. So if you want to see our information in writing, go check out the Beamex blog. And the Beamex blog is we try to keep it very educational. We're not trying to promote the company so much. And so you might find a lot of topics that we cover on the blog that could be helpful to you doing your work. And Roy's authored many, many blogs.
Ed, I read your blog every Tuesday.
Yeah, I haven't written that many. All right, so I jumped a slide ahead. Here we go. So getting back to the slide deck. So when you're doing loop testing, what kind of tolerance should you use? And, I'm not trying to pick on the manufacturer, the vendor of the equipment, but you don't necessarily want to use manufacturer specifications. You can use manufacturer specifications as a guide. Keep in mind, most manufacturers are stating sort of a pure accuracy. It doesn't consider long-term stability and other components of error, repeatability. Also, what is the reference standard the manufacturer uses to verify their equipment is also another parameter that should be considered. So I guess what should you use? If we say don't use it, you should use your common sense. And it really is, to me, it's a collaborative decision on what kind of error do you need to make good product, and not only high quality, but do it safely without endangering anything or pushing something to the edge where it could cause a bad failure. And it's really it's from your instrumentation and electrical group, your control people, and the maintenance people, because when you set a tight tolerance, that's putting pressure on the maintenance people to it makes it more expensive or more timely to meet a tight specification. So really try to strike a middle ground with all the parties and come up with something realistic that meets your requirements. So when you look at a loop, and we'll stick with our temperature example, keep in mind that the loop is no more accurate than the weakest component. So if we look at an RTD sensor, they vary in accuracy, but let's say the one we're buying is within a half, you can say it's generally within a half a degree Fahrenheit. Transmitters are very good. They're maybe even better than what I'm saying here, but typically they're 0.1% of span would be, pretty fair analysis. And maybe it has some turn down, so the span can be anywhere for the setting could be anywhere from 50 to 250. So a 10th% would be 0.05 degrees to 0.25 degrees would be sort of the expected error of that transmitter. And then the DC input cards, they don't typically drift, but maybe their accuracy is 0.25%. So here's the three different elements in our loop, and we've determined they have three different kind of errors, and the RTD is specified in Fahrenheit, and we had to convert from percent of span to a degrees F value. So in this case, if we take the 0.5 for the RTD, we square it. We take the percent of span tolerance, the tenth is 0.001 times a span of 200, and square that number. And then we're missing in the parentheses, we need to take the 0.25% times 200 and square that. You add those three numbers together, take the square root, and we could say that, the RTD is a half a degree, but the other two elements, the transmitter and the DCS input card, add another 1/4 of a degree of potential error. So that's one way to analyze a loop tolerance. So and if you look at the weakest link in this example, the 0.75 compares logically to the 0.5 RTD. The other two elements don't necessarily add the full amount of error. But some people are real conservative, so just add them up. So the idea is that if the RTD was off by plus half a degree, the transmitter was off by plus 0.2 degrees, and the input card was off by another half degree, worst case, we're still within 1.2 degrees of true measurement. So really those are two ways to analyze multiple components that make up a loop. And I would say the RMS is very well known, and it's, I like to say it's a statistical average. You're averaging the numbers in a statistical manner using this root mean square method. There's other considerations, and I already kind of mentioned this. The tighter the tolerance, the more expensive it will be to make the measurement and to maintain the measurement. So if it's a real tight tolerance and you're adjusting all the time, you're having to go out there more often to catch it before it becomes a problem. Keep this in mind that you set a tight number. If it's not realistic, it's not something that you really need, you're causing unnecessary stress to the maintenance people and maybe unnecessary expense. You're having to use dead weight testers and buy expensive tools to make these good measurements. So it comes back to trying to strike a balance. And just as an example, since we've been talking about temperature, a dry block, a good dry block, one that you can buy, just about anywhere, in general, they're within a half a degree, and it depends on the actual temperature. Higher temperatures are not this good. But, if our RMS average was 0.75 and we want a 4-to-1 ratio to meet this 0.75, we need something that's around 0.2 degrees. So this is an example where it becomes more expensive. So you can buy a reference probe, I'm calling it an RPRT, and you drop that into the dry block, and that does help you meet this 4-to-1 test uncertainty ratio. So here's something that you have to keep up with, maybe the parameters on it, the coefficient numbers. It adds a level of complexity. These things cost anywhere from $500 to $2,000 on top of what you spent for the dry block. So here's where we said, well, our loop error came out to this, but in the scheme of things in our plant, if our temperature is within 2 degrees, we'll get good reaction, we'll get good, control. So in that case, if the control engineer said 2 degrees was accurate, then now you have 4-to-1 by just using the dry block. So this is an example of where you can, for a relatively reasonable cost, achieve better accuracy, but it causes more stress on the maintenance people. And if you could get by with 2 degrees, it makes life a whole lot easier and allows you to perform the work faster and make it less complicated for your personnel. So when we look at loop testing, one thing, when you pull a probe out of the process, like a temperature probe, you're making a physical change. Do you reinstall it properly? These are things that, you need to weigh. Is it worth pulling that probe out of the process? Does it cause more harm than good? But in general, if you're doing loop testing, your management's going to have a much higher level of confidence in what you're delivering in the terms of measurement. And it's really the most accurate way that you can run a plant if you're doing end-to-end testing. And really, people can't argue about it. If you get into these arguments, hey, you need to check this or check that, you can say, well, we've done it, and there's something else going on. The valve, is out of control or needs to be rebuilt or something. It's not a measurement that you're making. Also, when you do a loop test, I say you're touching that instrument. You're really not, but by going through the transmitter, through the DCS input card, you are sort of verifying that those things working together are accurate and within your requirements. And if you're documenting your calibrations, you can start looking at your cycles and are things in control. You can back off maybe on the calibration cycle. For those things that are causing you problems, you can maybe increase the cycle on a few things that are causing you real bad headaches. So the whole thing is to try to help you become, proactive by doing these tests, get ahead of the curve and catch things before they become a problem. So those are, these are maybe reasons why you should consider performing a loop test here. And then, Roy, I don't know if you want to chime in on this slide, but, we've done a temperature loop today. You saw Roy do the demo, but it works the same for pressure. It's maybe a little bit simpler. You just use a pump or a pressure source and run the transmitter through its range, but see the readout. In the control room, it might be flow. It could be, if it's a differential flow, you could be looking at gallons per minute versus the pressure you're applying in the field. And these multivariable transmitters are complicated instruments, but they're really eloquent. They do a great job. And, we're calling it a loop test because there's three values that go into a calculation to generate the flow measurement. And you should try to check those things together and make sure that it's, making an accurate flow measurement. Most people aren't documenting their valves. They check them out and make sure they're stroking properly. But, you think about it, you're doing a loop test if you're sending current into the I to P and then looking at the milliamp output or feedback, or you could be looking at the heart percent travel parameter, or be looking at the field bus value, if it's Profibus or Foundation Field Bus. So in essence, a valve is a kind of a loop that you're checking. And there's different kind of flow elements, and when you're looking at just like a DP flow meter, you should also inspect the physical components that make that flow PV. So in the case of DP, you want to make sure the orifice plate isn't damaged or corroded. Look at the other physical things that are in the process. And then here's SIS. We had a question on this. and I think I said this. I said when you're checking out a safety system, I think it's best practice to try to do an end-to-end test on those components that make the system actuate. And you also, when you're doing an SIS, you want to try to do quick and simple things, not to make it real complicated. I don't know, Roy, do you have any other, we talked about you chiming in, but do you have other examples?
Before we do this demo, all right, so fine, I'll share my screen. And so you all know that I'm in Colorado, and some things are legal in Colorado that aren't legal other places. So I kind of think they want to turn Colorado into a new Amsterdam, sort of. And I get drug tested every week, just so you know, and I've yet to pass one of those. So if any of you guys can give me some heads up on how I can pass one of those tests, it would probably be helpful to me.
Sorry.
And now, yeah, you guys never should have unmuted me. I don't know what you were thinking. So we have a pressure calibration here. I've got a pressure pump as my pressure source. The transmitter that I'm using, let me see if I can show you this. So this is a Rosemont 3051 differential pressure. I'm hooked up to the high side. I've got the low side vented to atmosphere. And I'm powering it with the calibrator. And this is a loop test. I'm generating pressure at the input, and we're going to record what the output is at the DCS. All right? Before I hit start, let me zero out my pressure transducer. So my pump is open. Let me hit the 0 button. My top left is how much pressure I'm feeding. Let me hit start. I've got 0 pressure in. Let me check my DCS. 1.91. So my DCS is recording 1.91 inches of water. Let me accept this point. The bottom right is telling me where to go next. This transmitter is 0 to 207 inches of water. And it tells me to go to 51.75. I'm not going to worry about getting it exact. So I've got 51.64 in. I've got 5348 on my DCS. All right, and I'll accept this. So it doesn't matter that we get exactly on the 51.75 on our input, because we're doing a calculation of the output against the input. So whatever we're feeding it, we'll calculate it against that live reading that we're getting at the DCS, or on our 4 to 20 if we're doing just the transmitter. So, Ned, I don't know if you can see this, but my test points are red, and I'm thinking that's bad. 106.
Yeah, you're bad. You are bad, Roy.
106.96, really? Okay, 106.96, and I'm outside of the blue lines, which is my allowable tolerance. So right now I have 3 failing test points in a row. So what do? As long as everything is connected correctly, I need to go to 155 now. As long as everything is connected correctly, then I just way overshot it. Then we need to grab the test data as it is. And you know what? 163.79. That's what I'm showing on my DCS, and you can see that it's a similar offset all the way across the bottom. Let me accept this point as well. And it's telling me that I'm outside of my predefined range, that gray bar. But that's okay. As long as it's not a violation of your SOP or your standard operating procedure, you can calibrate how you like. All right, so I overshot it, my 207 a little bit. I'm showing 210.13. And just so you know, Ned would come in here and he'd be dialing it back in and getting it perfect and beautiful, but I'm the good example of a bad example, so I'm going to accept this point. Oh, I failed. All right, Ned. Fine. So I'm totally out of the blue. I really am out of the blue. Here's all my numbers. I was almost a 1% a span out all the way across, and my significance reflects that as well. I'm almost double what I was allowed. So what do I do? Trash can?
You're really bad.
I'm really bad.
Yeah.
So you may have a thought to trash can this and to hide all the evidence that you just failed the test, but that's not what we're about. We're about recording your as found as ugly as it is. We'll fix it, and then we'll record an as left. So let me save this. I'll save it as found. And let me go back. So this was my loop test. I've got 0 to 207 pressure input, and I'm keying in what the display on the DCS is showing to complete my loop. I've got a failed test in here. Let me back up one more. I've got another test on this. So PT702 is this pressure transmitter. I've got an offset. I don't know if there's an offset in my DCS or if my transmitter is out. So troubleshooting-wise, my next thing to look at is I'm going to do a calibration on the transmitter itself. I've got that preloaded. It's right here. It's really easy to load a calibration from your calibration software, a test for the transmitter and a test for the loop, and you run the ones that you need to. Let me run the transmitter test. Okay, so pressure, I need to be hooked up here on the top left, which is up here. I am. To power it up, I need to be plugged in here where it says loop. And it's a square root transmitter. Okay, let me hit X. So I'm still pressurized. You know what? This is interesting. I haven't even vented my transmitter yet, but it says I'm at 208 inches of water, and I'm at 20.1 something milliamps, but my error is still 1% off. That means that my problem is really in the transmitter itself. And this proves it without me even gathering data. But let me vent this out. I'll capture data on the transmitter because that's what I need to do. Let me just zero this guy out, and I'll hit start. So my first test point is 0, and I'm expecting 4 milliamps. I've got 5.5, which is about a 1% error. So let me close my vent. And what I'm going to do is I'm just trying to get it into the gray bar. This is a predefined area that I've already set up, which is 4% of my target. This is not the tolerance. This is how big of a target. How close do you want to get to my test point? My test point on the bottom right? Well, now it changed from 103 to 155.25. So now I'm going to get within 4% of 155. I'm just going to get it in the gray bar and let it go. Once it stabilizes, I've got a 5-second countdown, and I'm at my final test point. I overshot it a little bit, but I'm just going to, this makes a lot of sense. I've got about a 1% error, and yep, done by Roy, and it's flat all the way across. So, throw it away, save it. Save it. So I'll save this, and this is going to be an as found on just my transmitter calibration. So what do I do now? Now I need my heart screwdriver. Oh, that was a trick. So to calibrate heart, we use a communicator. And to do that, I'll click the secret button. That's up on the top left. Start communicator. This is where we'll do any trimming. And the manual on the 3051 says to start at 0, so I'm going to get a head start and vent my pressure pump. I've actually tried to save time and calibrate my upper level first and then do my lower level trim, but it always it seems to mess it up a little bit. So I do what the manual says, and I do my lower trim first and then the upper. All right, PT207, here we go. Click online. service tools, routine maintenance. Okay, pressure calibration. This is the cal on the sensor. So this would be the input side of the transmitter. Analog calibration would be the D to A, the digital to analog conversion, or the back half of the transmitter. In my experience, 90% of the time the problem is on the sensor side or the input, so I'm going to go to pressure calibration. I could do an upper, a lower, or a zero. Well, we already know the manual says do the lower first and then the upper. Now the zero, we're not going to do. Even though the zero is still on, is still zero, I'm going to set up the lower itself. And in some of our other webinars, we've talked about the actual difference between lower and zero. Warning, loop should be removed from automatic control. At zero input, we have 5.5 milliamps. Please note that. So it says apply low pressure. My low pressure is zero. You know what? I could click on that and re-zero this again. I've got air movement in here, so I might not be able to get it any closer. All right, that's as close as I can get. Now, everyone, watch the 5.5. I'm going to hit the check mark and... All right, so keep watching. Window 2. It's stable now. So I'm telling it that I'm at zero. Actually, this is where I tell it. I got a little ahead of myself. So I need to tell it I'm feeding you zero, so you should change this to 4 milliamps. So I'm going to hit the check mark, and it's self-correcting. So I've told it I'm feeding you zero, and it's really zero, and it made 4 milliamps the answer. So let me hit the check mark. Loop can be returned to automatic control. Now I'm waiting for these red letters to go away. This means that the transmitter is executing a method, and the microprocessor is active, and the transmitter won't even listen to me until that goes away. All right, so it's gone here. Now I could do an upper trim as well, but the fact that my offset was pretty flat all the way across tells me that it was a zero trim issue. Ned, do we want to do an upper or see how we are with the lower?
No, I think it works the same. You would just pump it to 207, and it's going to read 207, so we'll just save time today and pretend we did it. How about that?
All right. So let me hit the X on here. If the error would have been some kind of diagonal line, then I would hit the lower and the upper. If it's a flat line across, that means it's a zero shift, and we should be able to fix it by trimming just the lower. And so here we are. We just did our trimming. So we did our as found, it failed. We trimmed it, and now we're going to do the as left. Right now we have 3.9997. Let me hit start. I've got my 5-second delay. It's already stabilized, and my error is good. I'll take it up to my 25% point or so. Error, we're getting about 0.02%. And again, I'm just getting it in the gray bar and letting it go, letting it stabilize, and I have it to set to automatically accept. So we have a little bit of rise at the 50%. I wonder if that'll maintain or if it'll go back down. So what this tells me is that there's a natural hump in this transmitter, and we would have not received any benefit by doing an upper trim. 0.03% of span error. Passed. On a note, I could put so my typing is performed. Lower trim. This will be part of the record. Here's our graph. These are the numbers. And I don't think I put in any environmental in that front part, did I?
No.
All right, I'm going to say
you went from really bad to really good.
Well, you sound surprised, Ned. Don't think I like that tone. So it knows there's an as found already, and it's asking if we want to combine this with that one and save it as left, and that is yes. Let me hit the check mark. And one thing I could do, I could go back here and let me show you physically on the calibrator. This is how we left it. If I hit the secret button, I can do show older result. This is how we found it. It's way down there at the bottom, almost 1% of span out. I can hit the secret button again and show the newer result. And you can look at these at the same time on the same printout if you want to inside the software, but this way we don't have to unload it to look. And there's one final test we need to do. If only I could think of what that was. Ned?
Got to do the loop.
All right, we got to do the loop again. So we'll do an as left on the loop. And my transmitter is rebooting because hopping out of the test, I stopped providing power to it, and now it's booting up again. So let me do this. All right. So whether to re-zero or not is a question mark. What do we got? All right, it's almost done booting up. And I'm using the display on the transmitter as my theoretical DCS, just so we're dealing with real numbers here. Okay, so it's showing 0.0, so I can hit start, and I'll accept this first point. All right, so I won't get it exact here, but I'm reading 50.61. All right, I'll accept that point. All right, so I overshot my 103.5. I've got 105.79. All right. So again, the top left is what we're reading from the pressure pump. The top right is what our DCS is showing. Just waiting for it to stabilize here, 155.46. And final test point, here we go. Letting it stabilize. All right, so I'm getting 206.82. Okay, this is our loop check. We did it initially and it failed. As a troubleshooting method, we went to the transmitter that was in the loop, did a calibration, found out that that was out, we trimmed it, we did an as left. Now we're back to the loop test, and we passed. Holy moly. So our loop test came across as good. That means that everything inside of it is on the up and up. And let me hit save here, and I'll save to this as left. Check. Okay. We calibrated the loop, and then we calibrated the transmitter itself. We have an as found and an as left on the loop as well as on the transmitter itself. So we have proof what exactly was out, and we fixed it. And then now the loop is acting exactly as we had anticipated. So with that, I guess we'll go to Q&A.
That was great, Roy. I mean, I would say,
and it was even in front of people.
Yeah, but you know, how often does a loop fail? You know, I'm going to say 80% plus of the time, your loops are going to check out. You're not going to have to make a change. But in your example, the transmitter, for whatever reason, had a zero shift on it, a huge zero shift, and you quickly fixed it and fully documented not just that the loop was left in good shape, but you know what was the problem that it took to fix it. So yeah, so hopefully that gives everybody an idea of, you know, the first test was a temperature loop. We had the issues, can you pull the RTD in or out? And then on this test, we had a failure of the loop test, so you had to break the loop down and check at least one component to bring a correction about. Really, those are sort of some classic examples of what you might encounter in doing loop testing. All right, so I guess before we get into our final Q&A session here, we'd like to ask another poll question, and we kind of want to see what you guys think after watching all this, but we were at 75% of you are doing loop testing, and look at that, we don't have a single no. So, all
right, I'm going to vote no. Just a minute.
Yeah, get on there. So good. That was very interesting to see. We appreciate your feedback, and it looks like people were listening. So great. All right, so let's move on. I guess we have one last slide. You know, what are the takeaways of what we presented today? And for those of you that are just checking transmitters, yes, those probably are some of your biggest culprits for measurement error, but it's not enough. And not testing the temperature probe could cause you bad problems. So you at least need to do some spot checking, or at least address those somehow, that they're in the ballpark. Also, your input cards can drift. Yeah.
Ned, I've almost gotten into a fist fight a couple times talking about temperature probes, and I mentioned the fact that they drift, and I get some pretty intense comments that either they work or they don't.
Yeah.
So I've seen them where they were off by 1.5 degrees, or so. I guess what do they drift, or do they either work or they don't?
Well, I mean, they drift and then they fail, depending on the conditions of your process. But yeah, you can't calibrate a probe, so it's
true.
To fix it, you got to throw it away and put in a new one. But you should even kind of check the new one and make sure it's not, there's something else going on that's causing a problem. You'd catch it when you install the new one.
That's true. I guess I just want to put to rest the fact that there's a misconception that a temperature probe is flawless or it doesn't work. And that's simply not reality. So
yeah, I think you can get, if you're throwing them away, I don't know how much they cost. Let's say you're throwing away a $100 probe. If you could adjust your transmitter and get more life out of them, you save $100. But if they're making a bad measurement and it causes you to lose $1,000 or thousands of dollars of product, yeah, throw the probe away. It comes back to that common sense approach. Do what causes the least harm. So another takeaway, if as a maintenance professional, if you're delivering good measurements to the control room, then the engineer there can make good control, and you operate smoothly and efficiently and safely. So it's almost your reputation. If you're delivering good measurements to the control room, your maintenance department's going to have a good reputation with the rest of the plant. I feel that loop testing is underutilized. People, misapply it. Do keep in mind that doing a loop test might cost you more time, but if you've been testing individual things all along, it can save you time. So just again, try to make the argument that you're checking this loop, it's making good measurement. Let's move on and
do what makes sense.
Right. And we're all under pressure to get more done in a day. So utilize this method if it can help you, maximize your efficiency and how you operate. All right. Well, let's see. I see we have a few more questions. Oh, got one. We got. I guess just don't forget about ACE, September 18th and 19th in New Orleans. Be there. Roy and I will sign autographs. I don't know.
Yeah. So ISA is kindly donating MC6s and equipment to our lab portion, and I think Joe might even be on the line. He's going to be doing a multivariable demo live. How to calibrate a multivariable live and in person. And the annual calibration exchange is not a commercial thing. There aren't commercials in it. It's all about calibration knowledge and sharing. So it's not about self-promotion.
Right, and you can put on your resume or with your human resources, you can get classroom credit for the time spent. So hope to see you there in New Orleans.
Online. Yes.
There you go. All right, so here's this poor guy.
Room.
Yeah, this poor guy needs help. So I'm looking at a question about, and this is kind of our initial application, Roy, RTDs embedded in a motor. How can we verify right operation for this device? So one thing you could do is you could document, you could make a single point recording of each RTD measurement, document that, and let's say they're within a half a degree today, and however often you go out there and check them, if you're seeing them get wider and wider, next time you go out, they're 0.7 degrees, and next time they're 0.9 degrees, you're starting to see a trend. Chances are one of the probes is degrading faster than the other one. So maybe you need to figure out which one's right, and then look at the expense of replacing them or coming up with another way to measure that temperature. So that would be the best thing I can think of. And the question also says when we measure the resistance on the RTDs, they turn around and simulate that resistance into the PLC to see what the PLC is reading. I guess you can make an offset or a change on that. But I would do, instead of resistance, you could with our calibrator and a lot of process calibrators, you'd measure the temperature, which is the resistance, and then simulate the temperature into the PLC. I would do a 3-point check around those temperatures and maybe trim the PLC so that no matter what temperature's coming into it, it's displaying, an accurate temperature.
And that's an advantage of treating it as a loop.
Yeah.
You got one thing off, you make the opposite adjustment on the other end.
Yeah, I would say there's no point in simulating the exact resistance, that as long as you're in the range. We have a good person asking about mathematical concerns, extra uncertainties to add to the calibration check measurement. In my example of the loop error, I was using half a degree and percent of span, tenth of percent, quarter percent. You should, when you come up with those numbers, you should consider other uncertainties. I'll use quotes. I can't get in this, that what's the long-term stability? Most manufacturers will state a 1-year or 6-month stability type of parameter, repeatability, hysteresis, linearity. Those should all be added to the base accuracy statement, and coming up with a number that's the tightest number you could mathematically apply. So send me an email with a specific example. I'd be happy to answer that question. That was from Adam. Let's see. Here's one. This person has an RTD range of 0 to 160, but the dry block only goes to 150. This is a great question.
Yeah.
It's okay.
This is real.
It's okay not to check the last 10 degrees. If when I use a dry block, I like to check the normal operating temperature as my middle point, and then do a window around that operating temperature that represents, what's the lowest your process will ever run and what's the highest it might run. So if you're, in this case, your RTD it's going to put out 4 to 20 from 0 to 160, but you could check it at like 100, 125, and 150, something like that. You're checking the upper window that's, if your process normally runs around 125.
And the logic behind that is that when you plot 2 points or you plot 3 points, you should be able to draw a line, and that you should be able to extend that line and know what it would be at 160 degrees.
It'll still be accurate. You just haven't tested it or calibrated it at that point. But if you're within 1 degree at 150, you're going to, and you're flat, you're flat across the spectrum. You can say I'm no more than 1.25 degree at 160 or something like that.
And if this is a safety system, then okay, that's a little different. But if it's just a process temp that you actually aren't going to hit 160 anyway, then save time. Yeah. So we are.
No need to buy another. Another dry block to get those 10 degrees if you can justify it.
All right, we are at our end time, so maybe we just grab a couple more and then finish up.
Yeah, we are. Yeah, we only have a few more here. This is Leo saying that he has a dual pressure transmitter, if you have a dual pressure system, you got to calibrate both pressure measurements. It applies to the dual RTD. You're just going to have to, you almost have to consider it as two devices, even though it's one thing. It's really two functions by the one device, right? And here's somebody asking about a multivariable. How do you do a loop calibration multivariable?
Ned, how can you do a loop calibration with a multivariable transmitter?
That'll take me about an hour and a half. I can cover that.
You know what? I could.
But you know what? We're going to have, at ACE, we're going to have an expert there. And I do want to write a blog. I want to update. I've done a multivariable presentation that's recorded. You could watch it, but it's kind of dated. So I would like to do maybe watch our blog, and maybe we'll have some good information some new information about doing a multivariable. And let me see where I'm trying to jump through here. So here's a scenario from Justin. Your RTD is drifting positive 2%, but the DCS at the same time is drifting negative 2%. So then the indication is spot on during the closed loop cal. And so Justin wants to know, am I not worried about drifting of these two elements? Not really. If it was a safety system or something really critical, you could make the argument, but this is the point of doing a loop test. From end to end, you're getting a good measurement. It's like, don't touch it. It's not broken. But if you've discovered this, like in Roy's example, he saw the 1% off, but if you somehow discover that, hey, my primary element's 2% this way and my input is 2% that way, you got some bad problems with your instrumentation. Like, how did that happen? You need to address that so that you don't have that phenomenon. But that, I guess you're just lucky if that exact thing is happening.
Yeah, good question, Justin.
And so this is from Reese. This is a good friend of mine. The error is not the same over the range. It gets larger away from the ice point. So, I think, when we show our error graph on the calibrator, Roy was showing like a flat line. and that's really not always the case. Many times you'll see a slope. You'll see a low, a low to high, or the other way, high to low. So in Roy's example, all he had to do was fix the zero shift, and to save time, we didn't do a span adjustment because we knew it didn't need it. But I would say more often than not, you need to do both a lower trim and an upper trim and correct.
Agreed.
So the lower trim is your zero shift, and then the upper trim is really, in effect, is the slope. You're correcting it if there's a slope in the calculation.
Yep.
Okay, man, we have a few more questions, but I think, Roy, we need to wrap it up. Roy and I will split these questions up and try to respond in writing to you folks. Pass the word on to your friends that this will be available on the ISA website to watch later. So feel free to check this out again. And if we didn't say something clear, let us know. I think the next slide, does it show so there's our contact information. So we do have a survey that's going to pop up. Please let us know what you think of our topic today and what kind of topics you'd like us to cover down the road. We want to make this for you.
We really need that feedback. Yeah, we really need that feedback.
All right. Well, thanks, everybody. Appreciate you watching.
Nope. Ned and Roy, thanks.
Anything else, Mike?
Tremendous presentation today, just wanted to say. And also on behalf of ISA and Beamex, would like to thank you for your participation in today's event. Now, again, if you missed any portion of the webinar, would like to rewatch the recorded version, we will be emailing all registrants a link to the recording, along with additional links for supporting information, and included in that will be a link for ACE. Post-event survey will appear, as mentioned, requesting your feedback. Please do take a moment to complete this survey. It will help ISA plan future webinars. This concludes our program for today. Thanks, everyone, and have a great rest of your day.